Hello, my name is John Coonrod with Rogers Corporation, and I am a technical marketing manager. Today, I'm going to be talking about how RF filter performance can vary due to normal variation of material properties and also circuit fabrication processes and their normal variations. The agenda that I plan on following is shown here, pretty simple agenda. Basically going to be talking about material properties and their normal variations, as well as printed circuit board fabrication and some of their process normal variations. So to begin with, let's look at some of the material properties. Dielectric constant, which I'll call dk, is the same thing as relative permittivity or epsilon sub r. And the variation of that is something that the RF designer definitely needs to keep in mind. High frequency circuit materials are very well controlled for this property and for the variation of dielectric constant, but there still is some variation associated with the dielectric constant for any high frequency materials. Most of these high frequency materials have a published tolerance. So again, the designer needs to be aware of this and account for that in the design for the RF filter. Now, decay anisotropy and also TCDK, I'm going to talk about a little later. So let's move on to moisture absorption. Moisture absorption is a property that all laminates, all circuit materials have. It's basically how much of the atmosphere can be absorbed into the material due to atmospheric moisture or humidity, essentially. And materials with higher moisture absorption obviously going to absorb more humidity into the material. And the humidity will actually cause the material to increase dielectric constant and increase dissipation factor. So keeping that in mind is important for an application of filters that has, or working in an environment that is varying with humidity. Normally a moisture absorption property of 0.3% or less is considered good. In some applications that are very aggressive for varying humidity, then 0.1% or better would probably be desired, even though that's extremely difficult for a lot of materials. Now, glass weave effect, I'm also going to talk about in a few slides, so I'm going to skip that for now. Copper surface roughness, that's a topic that we've worked with for many years now, and that is the roughness at the copper substrate interface, and that roughness does vary from batch to batch of copper. So the circuit fabricator, the circuit designer should be talking to the material supplier and understand the nominal surface roughness of the copper it's being used, as well as the normal surface roughness variation. Surface roughness does impact the phase response and does impact the insertion loss of the circuit. And then CTE is the coefficient of thermal expansion. That's how much the material will physically expand or contract due to heating and cooling. And for some filters, the physical change due to CTE can be an issue. So if you have a filter design such as a very wideband edge coupled filter, then that means you normally have tight couplings. So the resonator elements have a very small space between them. And if that space varies much due to heating and cooling and the CT effects, then that can actually have a difference, or can make a difference on the RF performance for the filter. Now, quickly going through some of the variables on the circuit fabrication side, obviously the conductor width and the space between the conductors, in this case, it'd probably be the space between resonator elements of the RF filter. That can be a pretty big difference. And of course, there is some variation in making a circuit for how accurate the conductor width is etched and the spaces as well. And that will vary from batch to batch. So again, the designer should be talking with the circuit fabricator and understanding exactly what to expect for that variation. Trapezoidal effects, what I mean by the conductor trapezoidal effects is a lot of the software that we look at, we'll see in a cross-sectional view a signal conductor that is rectangular in shape. In reality, the conductor effects or the conductor shape is more trapezoidal, and that trapezoidal shape will change from one circuit to another, and some of that is due to the copper thickness, and the copper thickness will also vary from batch to batch of circuits. And the copper thickness is usually because it's a plated through hole circuit, and plating the copper through the hole also means that the circuit image gets plated thicker or thinner along with that process, and there is normal variation for that copper plating. So conductors can be thinner or thicker from one batch to another of the same design, and that thickness does have an effect on the trapezoidal effects and does have an effect on coupling, especially if it's a tightly coupled design. So again, a wideband RF filter with tightly coupled resonators, then the trapezoidal effects as well as the copper thickness variation can be pretty important. Solder mask is another thing to consider. Of course, in RF simulation, no solder mask is easy to simulate, and if you add the solder mask, it's a little more complicated. But the difference between having fields fringe in air with no solder mask and fields fringe through solder mask can be very significant, because the solder mask will add to the effective dielectric constant and add to the insertion loss. And then final plated finishes, I'll talk about a little later. And the layer-to-layer alignment comment is really more related to multi-layer circuits. And it could be like a strip line broadside coupled filter. Then the layer-to-layer alignment is pretty important. And again, the designer should be talking with the fabricator to understand what kind of tolerance should be expected for layer-to-layer alignment. Now, anisotropy, all materials have anisotropy. And most of the materials used in the printed circuit board industry are anisotropic. In other words, they're not isotropic. Anisotropic means that the decay is different on the x-axis, y-axis, and z-axis, z-axis being the thickness. I'm not going to go through this slide in much detail. You can read through the details if you'd like. But in general, the diagonal of the tensor, or the matrix anyway, is what's normally considered. So the epsilon sub xx, epsilon sub yy, epsilon sub z are the dielectric constant numbers that are considered. And due to formulation of these materials and due to test method, normally epsilon sub xx and epsilon sub yy are assumed to be the same value, which is usually a pretty good assumption. And also for test measurements, it's actually easier to test that plane as it is the individual axes. So normally we look at the XY plane, that's how it's reported for the anisotropy of a material, the decay of the XY plane, and the decay of the thickness axis or the Z-axis. Now, how that comes into play, here's an example of a microstrip edge coupled bandpass filter. And you can see in even mode, you have fields between the signal plane and the ground plane, and there are no fields coupled. In the middle picture and the right picture, you can see the odd modes, and in odd mode, you still have fields between the signal plane and the ground plane, of course, but you also have fields between the signal conductors as well. So there is coupling fields between the signal conductors, and those coupling fields are using the XY plane. So the dielectric constant XY plane are going to be altering these fields. Now I'm also showing the glass weave effect in a very simple way here. So the odd mode middle picture compared to the odd mode right picture, the odd mode middle picture has fields interacting with the glass, which is drawn in blue. So the glass reinforcement layer drawn in blue actually has a higher decay. It's usually about 6 decay or more, and the resin system is usually lower than that. So the fields actually interacting with the glass in the middle picture and not interacting with the glass on the right picture can make a difference in the effective dielectric constant of the odd mode, which means the filter, of course, could behave different. So this is pretty common when you look at the same circuit design from batch to batch and look at many different circuits, where one circuit, the circuit feature will align to the glass weave pattern differently than another circuit. Here's a list of many materials used in the high frequency industry, and just giving you an idea for how anisotropic they are. To begin with, the general rule of thumb is a material with a lower dielectric constant has less anisotropy, and that can be seen looking at the first row of material, the RO3003 substrate. And the Z-axis is about 3 dielectric constant, the XY plane is about 3.05, so there is a little difference. Not a huge difference, but there is some. And then as you go up in dielectric constant, looking at the materials on the second and third row, the RO3006 material and the RO3010 materials, you can see that the dielectric constant is much more different. There is higher anisotropy on the higher dielectric constant materials. That's not true with all high decay materials, but that is a general trend. Also, along with that general trend is materials that are glass reinforced typically have more anisotropy than materials that are non-glass reinforced. Now switching gears to talk about TCDK, thermal coefficient of dielectric constant. Here is some testing I did with microstrip transmission lines using the microstrip differential phase length method. And what I'm showing here is the circuits operating at room temperature blue curve, circuits operating at 65 C, and circuits operating at 125 C. These are all the same circuits, except they're operating at these different temperatures. Now the material that it's built on is a 5 mil thick substrate, and it is not a Rogers material. It is a competitive material. I_A is what I'm calling it. And it does have a poor TCDK, or in other words, the dielectric constant will change a lot with a change in temperature. And here you can see at 77 gigahertz, the difference of these operating temperatures causes a dielectric constant change of 0.031 at 77 gigahertz. That same testing with the material that has a very good TCDK, the Rogers RL3003 materials, nearly perfect TCDK of 3 ppm per degree C, 0 ppm per degree C would be perfect or ideal. So this is pretty close to ideal, and here you can see the differences of these circuits behaving at these, or operating at these different operating temperatures. Really isn't much. In fact, that's pretty much our measurement noise. So a difference of 0.001 in dielectric constant. So for applications where there is varying temperature, then the TCDK may be something worth considering. Now, let's think about the circuit fabrication side of things. On the circuit fabrication side, there is a concern sometimes with copper plating thickness. And as already mentioned, as the plated through holes plated with copper, the circuit image is also plated with copper. So batch to batch of circuits, the copper plating thickness can be different. And here what I did was an experiment using the same sheet of material, 10 mil thick, RO4835. It was 24 by 18 initially. I cut it in half, and one panel at 12 by 18 had circuits made with thinner copper. The other half panel had circuits made with thick copper. They were the exact same design, same materials, same everything. The only difference was the fabricator purposely plated the copper thin for some sets of circuits, or one panel, half panel circuit, and then plated thicker copper for the other half panel circuits. And here, if you look at the difference between the effective dielectric constant on the y-axis for the curve that is red compared to the curve that is blue, the red curve and the blue curve are tightly coupled grounded coplanar waveguide. So this is a circuit that is a 2 copper layer circuit with ground signal ground on top and a ground plane on the bottom. And that is a tightly coupled grounded coplanar waveguide. And the difference in effective dielectric constant is 0.1 when you compare the only difference of thin and thick copper. Thicker copper has taller sidewalls, so you have more fields coupled through the air. Air is a lower effective dielectric constant, so it reports lower. So tightly coupled has a difference of 0.1. If it's loosely coupled, which is the purple and green curves, now we get a difference of 0.075 in effective dielectric constant, basically saying a loosely coupled circuit feature is less impacted by copper thickness variation than tightly coupled. Now let's look at final plated finishes. Here I'm talking about ENIG, electrous nickel immersion gold. It's very commonly used. It's a very good finish, except it does cause some differences in phase response, and it most certainly causes differences in conductor loss and insertion loss. So here I'm showing differences in phase response, and this is, again, tightly coupled grounded coplanar waveguide circuits. Y-axis is effective dielectric constant, x-axis is frequency. The blue curve are circuits that were made with bare copper, no plated finish. Orange curve is ENIG with thin nickel, gray curve is ENIG with thicker nickel. And this is in the range of normal variation of nickel thickness, and you can see that the nickel thickness does make a difference on the phase response, which is related to the effective dielectric constant. So again, this is something that the designer should be talking to the circuit fabricator about on what to expect for variation of the final plated thickness. And then this is just a screenshot of these filters being tested on my P&A. Left picture is the filter and its performance for the bare copper circuit. Filter on the right is the exact same material, same design, same everything except with ENIG. And then a table of information below shows that we do see a little difference in center frequency, bandwidth, and Q, but you see a remarkable difference in loss, where the ENIG circuit is going to have much more losses than the bare copper circuit. Then going along with that same thought process is thermal issues. So as you're all probably pretty aware, more insertion loss means higher heat being generated. And in this case, I used edge coupled bandpass filters that are hairpin design and operating at 3.32 gigahertz, applying 25 watts. And you can see that there's a pretty big difference in operating temperature or maximum temperature. The image on the left is a thermal image of the bare copper circuit, maximum temperature 152 degrees F. The image on the right, a thermal image picture of the exact same design, same material, same everything. And the only difference is this circuit has ENIG plating and caused more insertion loss, therefore higher heat is being generated. Here the maximum temperature is 262 degrees F. So that's all I have for the topic at this time. I wanted to leave you with a screenshot of our Rogers Technology Support Hub and invite you to become a member. As a member, you can have access to free software, calculators. We have the Raj mobile app, Also have technical papers, video library, and you have the ability to contact the engineer in your area. Thank you very much and have a good day.